Hello, welcome back. The title of this lesson is called What is a Logarithm? Or I could retitle this thing Logarithms Explained or Understanding Logarithms. This is part one of several lessons on logarithms. A logarithm is one of the most important functions in all of science, in all of math. And I know I say this a lot, but really I'm trying to emphasize when I'm really trying to tell you things that are extremely important. And you'll run into logarithms in your chemistry classes, you'll run into logarithms in all of your physics classes, any engineering class, any math class, you're going to run into logarithms. So it's not every day I can teach you about a function this important. I remember the very first time I got introduced to using a logarithm in a chemistry class. I went up to the teacher because the pH scale, you probably heard of pH in chemistry, has logarithm in its definition. It's the negative logarithm of hydrogen ions in a solution. That's a crazy, complicated sounding thing, but basically it's the logarithm of a number, right? And so I went to the teacher and I said, what does this mean? Logarithm of hydrogen. What does log mean, right? And she said, well, that's a button on your calculator. And I love this teacher. She's a fantastic teacher, but she didn't understand at a fundamental, detailed level what a logarithm was. For her, it was just a button on the calculator to calculate things. I want to go beyond that with you. I want you to understand what a logarithm is. I want you to know intuitively why we have logarithms and why they so naturally fall out of math. Because the knowledge that you gain in this lesson will be applied to many, many, many courses down the road. All right. So before I get into what a logarithm is, I want to give you a little motivation. Just two examples. I already mentioned the first one, the famous pH scale. Acids and bases is so fundamental to chemistry. It's a logarithmic scale. So logarithms come into play anytime you calculate anything to do with pH concentrations in chemistry. Right? Another very famous example is the Richter scale of earthquake energy. You know, you have we say an earthquake was a 6.2 on the Richter scale. Earthquake was a 7.3 on the Richter scale. Earthquake was a 1.2 on the Richter scale. What does that mean? Well, a Richter scale is a logarithmic scale. So by the end of this lesson, I want you to understand what a log is, but also why do we use them for these scales? Why don't we just use numbers? Why do we have to use logs? So by the end of this, you're going to understand all of that. There are many other examples of logarithms. I could go on and on. In electrical engineering, we use them to plot frequency response of amplifiers and mechanical systems. There's tons of uses for logs. But for now, we want to go and learn what a log actually is. So in a nutshell, this is what a logarithm is. A logarithm is the inverse function of the exponential function, of an exponential function that we've already learned about. So I already told you exponentials are so incredibly important, and they are. So the inverse of those functions, which you've already learned inverses in the last lessons, the inverse of exponential functions is what we call a logarithm. That's why logs are so important, because exponentials are also so important, and they go together like peanut butter and jelly, basically. All right, so that's so important. I actually want to write that down. If you pull anything out of this, I want you to pull this. A logarithm is the inverse function of an exponential function. I don't always write definitions out, but this one's extremely important. So I'm going to keep that in the top. It's the inverse function. And if you remember, what is an inverse function? We already talked about that in the last lesson. Inverse functions go together like peanut butter and jelly because inverse functions can undo each other. If I have function number 1 and function number 2, and we know that they're inverses of each other, if I run a number through the function, calculate the answer, take that answer and put it through the next function, and calculate that answer, the number I get out is going to be exactly the same as what I started with, because the inverse function kind of undid or did the opposite calculation of what the first function did. So if I stick a 1 onto the input function, get the intermediate, run it through the second function, I'm going to get a 1 on the output. If I put a 2 on the input, I'll get a 2 on the output of the inverse. If I put a -5 on the input and run it through both functions, I'll get a -5 on the output. Whatever I put on the input, I'm going to get it on the output because the inverse undoes it. And that's not a technical word, it's my word, but it's a good word to use. So we know that a log, so you can use the full word logarithm, or you could just use the word log, can, quote, undo an exponential. So remember what an exponential function is, like 2 to the power of x or 3 to the power of x, right? If we run the number through that exponential function, take the output, and then stick it through the same similar logarithm, the inverse function, we'll get exactly the same thing as we started with, because it undoes, or it does the opposite of, that exponential function, right? One of the biggest uses of logarithms is we can use to solve exponential equations. I hate it whenever you look in a book and it explains what something is, but you have no idea why it's useful or even if it's very important. This one's super important because we can use logarithms to solve equations that have exponentials in them. Why? Because every equation we solve, we always have to do the opposite, right? The opposite operation to get the variable by itself. If you add something to the variable, you might do the opposite. You might subtract. That's, by the way, an inverse kind of operation. If you multiply in the equation, then you might have to divide to get x by itself. If you have a square, you might do the opposite, a square root, right? We've been doing this forever, right? But now that we know what an exponential function is, we might often have to do the opposite of that thing to get the variable by itself. The opposite is going to be what we call the logarithm. So that's why logs, one of the reasons why logs are so important. Now here's our roadmap. I'm going to write down the definition of a logarithm. We're going to work a few very simple problems so you know how to handle it. And then we're going to draw some graphs to show you that the inverse of an exponential really is a logarithm and what the graph of a logarithm looks like. And then at the end of the lesson, I'm going to go into a lot more detail about why we use logarithms in the Richter scale and pH and some other applications because I want you to understand why we care, because that's really the point of this thing. So here we have enough space. Let's go ahead and write down the definition of the logarithm. So here's what a logarithm is. A logarithm is the following thing. And I know it's a mathematical weird definition. I'm going to make it very clear for you. If the number b, this is a letter, but we're going to call it a number b, and the number n are positive numbers with b not being equal to 1, because b is going to end up becoming the base of the logarithm. And we already know that the base of an exponential can't be 1 because we talked about if you have a 1 as a base, you don't have an exponential function anymore. But anyway, if we have these two numbers b and n, they're both positive, but they can't be equal to 1. Base can't be equal to 1. Then we say that the logarithm using the base b of the number n is equal to k, right? And this is if, well, let's do it like this. If and only if I can spell only, if and only if b to the power of k is equal to n. So here is the definition of the logarithm. I'm going to leave it on the board because we'll reference it a lot. I know it doesn't make a lot of sense when you see all this jibber jabber everywhere, but I'm going to make it very clear. What I want you to understand, first of all, is that here is kind of a relation that involves this logarithm. I want you first to understand that the logarithm has a base. Here we put the letter b there, but in real life, they're not letters. The bases of logarithms are just like the bases of exponentials. For an exponential, remember the base was the number on the bottom, 2 to the power of x, the base was 2. 10 to the power of x, the base was 10. 5 to the power of x, that's an exponential, the base was 5. So for logarithms, we have bases also. So you might have logarithm with a base 2, logarithm with a base 5, logarithm with a base 10. Why do you have to have bases for logarithms? Well, it's because it's an inverse of the exponential function. So of course, if the exponential has a base to determine the shape, and if I'm just reflecting that graph over to find its inverse, that's what an inverse is, then the inverse, which is the logarithm, also has to have a base. And it's the same base as the exponential function that you are talking about. So we have an exponential logarithm base here. So what we have is a logarithm with a base of some number equals some other number. And the relationship of all this means you take the base to the power of whatever you have on the right-hand side, we're calling it k, is equal to some number. All I want you to know about this definition right now is that logarithms can be transformed into exponentials because you have the same things here, b, n, and k, b, n, and k. And these exponentials can be transformed into logarithms, b, k, and n, b, k, and n. So anytime you have an exponential, you can always write it as a logarithm. And anytime you have a logarithm, you can always write it as an exponential because they're inverses of each other. All right? So let's go through a couple of very simple problems that you'll understand very quickly, and then we'll ratchet up the complexity as we go and we'll draw some pictures to make sure you really understand. Let's say a real life example. Let's say we have the logarithm, if I can spell logarithm, the logarithm base 2 of the number 8. How would we calculate this? Well, we have a base 2, and we're taking the logarithm of 8. Here's what you do. To translate logarithms, you always have to translate them into an exponential because they basically can always be written in terms of exponential. So what you do is you say the following thing. Okay? You say the base, write that, to the power of some number, I don't know what it is, x, is equal to 8. 2 to the power of whatever the answer is that I'm trying to calculate here, that's what I'm trying to find. I'm trying to find the exponent, is equal to whatever the logarithm that you have here is. Now let me ask you, how would you figure this out? What is the exponent here that makes 2 to the power of that exponent 8? Well, this means that x has to be equal to 3. Sorry, x has to be equal to, if I can write it correctly, 3. How do I know that? Because 2 to the third power is 8. 2 times 2 times 2 is 8. So what I've basically said here, and just stay with me, is that the logarithm base 2 of the number 8 is equal to 3. And the reason I know that this thing is equal to 3 is because I'm going to triple underline it. It's because 2, which is the base, to the power of 3 on the right-hand side of the equal sign equals 8. 2 to the power of 3 is equal to 8. I'm going to run my fingers a few times. 2 to the power of 3 is 8. 2 to the power of 3 is 8. 2 to the power of 3 is 8. That is going to be how you translate logarithms every time you write them down. You say base to the power of what the thing is equal to 8. The thing you're trying to find in a logarithm, the thing that the logarithm gives back to you, is the exponent required to calculate this number. I'm going to say that one more time because this is the kind of thing that you learn after you do a lot of problems but is often not really told to you. The logarithm as its output gives back to you what exponent is needed to make this thing equal to 8 when I use this base. That is why logarithms and exponents are inverses. Look how I took this logarithm and I write it as an exponential expression. 2 to the power of 3 is 8. This is an equality here. 2 to the power of 3 is 8, right? I can also start with this and go backwards. I can write this as a logarithm for the same reason. The base is 2 of the number 8. The exponent 3 is what's coming back. So you're often converting back and forth between exponential form and logarithmic form. You have to get used to that. So let's do a couple more of these to make 100% sure that you are getting comfortable with it because it's the most important thing, okay? Let's say I have the logarithm base 2, and remember this base can be any number other than 1, but I'm just using 2 here, of the number 16. How would I figure out what the base, the logarithm base 2 logarithm of 16? How would I figure out what that is? Well, I have to write a little equation to figure out what that is. I know that the base of this thing to the power of something that this logarithm is going to equal is going to have to equal 16. Because logarithms return the exponent, it returns an exponent back to you. That's what logarithms do. And I'm going to say it a few times because I want you to remember that. Logarithms give you back an exponent. So 2 to the power of some exponent, that's going to be what this log is equal to 16. Now if you run through it, it can't be 2 squared, it can't be 2 cubed. X has to be equal to 4 because 2 to the 4th power is actually 16. So another way of writing this is the log base 2 of 16 is equal to 4 because, triple underline, the reason this is true is because 2 to the power of this exponent that the logarithm gave me back is actually equal to 16. You see, we're following the same recipe in both of these examples. 2 to the 3rd power is 8. That means logarithm base 2 of 8 is 3. The logarithm gave me back the exponent that's needed when I raise 2 to that exponent to give me this. And I can write it in exponent form like this. This one is 2 to the power of 4 is 16. 2 to the power of 4 is 16. That means the logarithm gave me back the exponent needed. So I raised the base to that exponent to give me that number. So it's literally a reverse exponent, a reverse exponential function. The exponential function is the base to the power of an exponent. The logarithm is like, okay, here's your base. Here's the final number that I want you to kind of have. Tell me what exponent is needed to give me that number. That's what the logarithm does. It gives you the exponent back. So you have to get in the use of saying 2 to the power of whatever's on the other side of the equal sign equals this. 2 to the power of whatever's on the other side of the equal sign equals this. I'm saying it a lot of times because it's literally the most important thing in this whole lesson. Right? Let's take a look at another one. What about the log base 2 of the number 1? What would that equal to? Well, I'm going to show you that that's going to be equal to 0. How do I know it's equal to 0? Well, it's because of the following thing. Because the base to the power of this exponent that the log gave me back is equal to whatever I'm taking the logarithm of. And I know that this is true because anything to the 0 power is 1, right? Make sure you understand that. Every time base to the power of this is equal to this. And that's exactly what I wrote. What if I have the logarithm base 2 of the number 1/2 is equal to -1? How do I know this is true? Well, I know it's true because the base to the power of -1 is going to be equal to whatever I was taking the logarithm was. Remember, the logarithm gave me the power back. And you know that this is true because 2 to the 1/2 means I can drop it in the denominator and make it a positive power, right? And so if I want to generalize this whole thing, 2 to the power of 3 is 8, 2 to the power of 4 is 16, 2 to the power of 0 is 1, 2 to the power of -1 is 1/2, I can generalize it, and I can say that the log base 2 of the number n is equal to k, and that's because 2 to the exponent k is equal to whatever this number I was taking the logarithm of. And don't forget that this base, and in all of these cases I'm using the number 2, but the base can be 3, the base can be 4, the base can be 10. The base can not be negative though, because remember, we go back to our definition. If b and n are positive numbers, but the base can't be 1, why can't the base be 1? The base can't be 1 because if you have 1 as the base of an exponential, then you don't have an exponential at all. 1 to the power of anything is just 1. And you can't have negatives for the base for the reasons we talked about in the exponential function because you don't have an exponential function there either. Go back to the lesson on exponentials if you forget that. So the base has to be the same kind of base as an exponential function. It has to be positive, and the base can't be 1. So it has to be bigger than 0, but it can't be 1. Now this definition should make a little more sense. The log base b of the number n is k, if and only if b to the power of k is n. b to the power of k is n, exactly as we've done it with numbers down here. Okay, so far I have shown you the mechanics of what you do when you see a logarithm on the page. All you have to do is say the base, which is written right underneath the logarithm, to the power of whatever the thing is equal to whatever you're taking the logarithm of, because the logarithm gives you the exponent back of whatever you're taking the logarithm of, right? But we haven't really done anything graphical. We haven't really shown you that they're inverse functions. We haven't really done any of that. So what we need to do now is draw a couple of quick pictures to show you that the logarithm is really the inverse function of an exponential function. And then you'll really understand more about why they're exactly so closely related cousins of one another. Okay, so why is this behavior happen? Why is it that 2 to the power of k is this? Why is it that 2 to the power of 0 is this? Why is that the case? Let's look at the following thing. Let's draw two graphs. This is the middle of my board. So I'm going to try to draw two graphs. I'm going to try to draw the exponential function right here. And then I'm going to try to draw over there, I'm going to try to draw the logarithm. So here I have f of x, and here I have x. And I want to draw first the exponential function. So what I'm going to draw as my exponential function is f of x is 2 to the power of x. Again, remember, I'm using the base of 2, but this base can literally be 10 or 5 or 15. It can't be negative, and it can't be 1, but it can be anything else. It can even be decimals. 1.3 to the power of x is perfectly fine as a base for this exponential function. But 2 is very easy because we can calculate things in our heads really, really easy with the number 2. Now, I think I need to draw some tick marks, and I need to try to be kind of precise with them. So here's 1, here's 2, here's 3, and here's 1, 2, 3, 4, 5, 6, 7, 8. Okay, I barely made it. That's as many as I need. Remember, every exponential with a positive base like this, a bigger than 1, starts off like this and goes up to the right. So we know this exponential function is going to look like this. We know it's going to go through the value of 1 because this is 1 right here, right? So we know it's going to go through here, but we need to be a little bit more precise so that when we draw the inverse, it'll make a little more sense. So what we're going to do is we're going to calculate 0, 1, that's going to be a value here. And then when we put the value of 1 in here, this is 1, this is 2, this is 3, we put the value of 1 in here, 2 to the 1 power is going to be 2. So it's going to be up right here at 2, right? Now we put 2 in here, it's going to be 2 to the power 2 is 4. So here's 1, 2, 3, 4. So it's going to be something like this. Okay. And then 3. So 2 to the power of 3 is going to be 8. So that's why I needed 8. 2, 3, 4, 5, 6, 7, 8. It's going to be 8. And then it's going to be something kind of like this. All right. So you see, it's not a straight line. If it was a straight line, it would be like this. But you see, it's curving. So what we need to do is attempt and I'm probably going to mess this up, but it needs to go something like this. It needs to go through this point, through this point, through this point, and then up. It's not perfect, but I'm not going to erase it because it's actually close enough. It goes through all of these points. Now I need to label some points because I'm going to draw these same points over in the logarithmic curve, okay? What do we have right here? Well, this point goes over here. It's 2 to the power of 3. That was equal to 8. The base 2 to the power of 3, it was equal to 8. That's why we landed right there. Okay, this one is, I'm going to save that one for later. This one right here is, over here, we can draw a little line right here. It's 2 to the power of 1. 2 to the power of 1, that's equal to 2. Now we know that this is 2 to the power of 2, right? So I can kind of draw this one here as over here. This is going to be 3 comma 8. This is 3 comma 8. And this one is 2 comma 4. And this one right here is 1 comma 2. And this is just the intercept right there, okay? So this one right here is 2 to the power of 2 is 4. But what I want to do is I want to introduce this notation. Notice over here I have b to the power of k is n. The k is the exponent. The base is b. N is the number you get out that the exponential calculates, n. So what we really have here is I'm going to say this right here is, and I know it's really the number 2, but I'm going to put the letter k underneath it. So really this thing is going to be something like k comma n. Why? Because 2 to the power of k was equal to n. Yes, I know it's at the number 4, but I'm generalizing it because I want to map it over. You'll see why I'm going to generalize it later. So it's really the number 2, but let's call it the letter k because any of these numbers can be k. I'm going to run it through. It's going to be 2 to the power of k. That gives me the number back. We know it's really the number 4, but that's pretty much what it looks like right there, okay? Now what we want to do is we want to draw the inverse of this exponential function. The inverse, remember, is the function that you get when you draw a diagonal line at 45 degrees, which is this line, y is equal to x, and you flip this thing over, okay? Now, I don't have room on this graph, so what I'm going to do is go over here and try to draw it right here. So here is this. I'm going to try to draw it as good as I can. I'm not going to probably do a great job. And this is not going to be f of x. This is going to be f inverse of x, right? The inverse function, which means that I have to draw kind of this diagonal line here, which I will do as a little reference. It's going to be a diagonal line, and this diagonal line is the equation y is equal to x. And we're going to essentially, you have to pretend it's here, and you map it, and you flip it over, right? So how many tick marks do I need? Let's try to use the similar colors. Let's go, if you think about it, this is going to flip down, so you need 8 this direction. 1, 2, 3, 4, 5, 6, 7, 8. That's 8. And then let's just do 1, 2, 3, 4. All we need, I think, is 4 in this direction, like this. All right? So what's going to happen is this thing is going to get mapped over here. So what's going to happen is, let's extend this guy down just a little bit. Remember, the inverse function takes all of these points and it interchanges them. This point gets interchanged. This point gets interchanged. That's how the mapping happens. So we know that 0, 1 is here. So that means it needs to go through 1, 0. 1, 0 right here. Actually, let's do it right here. 1, 0. It needs to go through this point right there. 1, 2 is a point. That means 2, 1. 2, 1. This needs to be a point because I flip it around. 2, 4, that means 4, 2 needs to be a point. 1, 2, 3, 4, 1, 2 means this guy right here. 1, 2, 3, 4. Whoops, I did the wrong one. It's right next door, right here. 1, 2, 3, 4, 2. And then 3, 8 means flip it over, 8, 3. This is 8, 3. This point needs to be in right here. So all I tell you is take these, I flip them around, you draw the points, and then you can kind of see that it's going to bend over like this. So if I can do a good job, which I probably can't, it's going to go through like this, bend over, and go something like this, which actually is not too bad. I kind of messed up the end there. You get the idea. It goes something like this. That's not too bad. And if you use your imagination, you can see that this thing reflected over is the exact inverse because it's a flipped over version of this thing. So this equation down here that we've written down is not 2 to the x. This thing is called the inverse, right? And it is log base 2 of the number n. Remember, you're taking the logarithm using a given base of the number n, and what does it give you back? It gives you back the exponent. The exponent such that that base to that exponent is that number. You're literally going backwards. It's like the logarithms, we never calculate the exponent. That's just never done, but logarithms do that. They give you the exponent back, right? They give you k back. They give you the k, which is the exponent needed when you raise it to the base to give me this number right here, right? So every number I put in here, the logarithm is giving me the exponent needed back, right? So what are these points here? Okay, this point means that I put 1, 0 in there, which is exactly the mirror image of this guy, okay, or the flipped value of this guy. It gives me the exponent back. In other words, if I'm going to take the logarithm base 2 of the number 1, the exponent that I need to do that is a 0, because 2 to the 0 power gives me 1. Okay, this point right here is 2, 1. Because if I'm taking the logarithm base 2 of the number 2, I'm going to get a 1 back. I need an exponent of 1 to do that. Okay, this guy is, I'm going to write two things down. It was 2, 4. It's really 4, 2. However, I'm going to also write it as, instead of k dot comma n, it's n comma k. Because what I'm doing is I'm putting the number in that I want to take the logarithm of, and it's giving me the exponent back. In this case, the exponent was 2, but in general, it's giving me the exponent k back. And then this last one here is, instead of 3, 8, it's 8, 3. So remember, what did I say exponential functions do? I'm sorry, what did I say inverse functions do? It undoes, or it does the opposite of the original function. So if I have a function here, number 1, and a function here, number 2, and I put the number 1 in there, then I'm going to get some value out. And I take that and I put it through the inverse, and I'm going to get some other number out, but the number I get out will be exactly the same as what I put in, because it kind of undoes the function, the first calculation. If I put a 2 in and run it through both of them, I should get a 2 out. If I put a 10 in and run it through both, I should get a 10 out. So let's look at that. In this exponential function, if I put a 3 in as an input, I'm going to get an 8 out of this exponential function. But if I take this 8 and I put it through the second function, I'm going to get a 3 out. 3 is exactly what I put in to begin with. If I put a 2 into this original function, I'm going to get a 4 out. But if I put that 4 in here, I'm going to get a 2 out, which is exactly what I started with. So you see, these are inverse functions, because whatever I put into the exponential function, and then I run it through the inverse, which is the logarithm, with the same base. The base has to be the same. What I get out is exactly what I put in. And that means, of course, this is a mirror image reflection of this thing here. So you need to remember two things about this graph. Number one, this is a logarithm. It gets infinitely close to the axis here. It's an asymptote, but it goes off to infinity this way, but it bends over very, very quickly like this. Okay? Whatever number you put into the function, it's giving you the exponent out needed, so that if you run it backwards through the function, you kind of get what you started with. And then, of course, it's a mirror image reflection of this exponential function. So these guys, inverses of each other. So we don't say that this is just the log is the inverse of the exponential. We also go the other way. We say that the exponential is also the inverse of the log. They're inverses of each other, and they undo each other. So if you have an equation that has an exponential function in it, but that variable is wrapped up in the exponential function, you want to kill the exponential, you might take the logarithm of both sides, because the logarithm is going to kill the exponential. It's going to disappear because of exactly what we said here. Inverses undo each other, right? If you have the other situation, you do the other operation, like if you have a logarithm on both sides of an equation, or on one side of an equation, but your variable is wrapped up inside of the logarithm, but you want to solve for the variable, you got to kill that logarithm. So you raise both sides of the equation to the exponent, base to you basically have to raise it to an exponent to kill the logarithm, and it'll disappear and your variable pop out. We'll do that later. We'll solve equations using this property here. The bases are the same. That's the other thing I want to point out. In order for this inverse business to happen, the bases are the same. Right? The base 2 to the power of x, the inverse of that is the base 2 logarithm. And the bases have to be the same. Otherwise, they're not the same thing. And that's why when we solve logs, when we do this business with solving logs, we end up writing it as an exponential function because they both kind of go together like that. And any log can be written in exponential form, and any exponential can be written in terms of a log form. Because what's happening in this log equation is I'm just giving you a number and getting the exponent out. When I go to this equation, I'm giving you the exponent and I'm giving you the number out. So it's literally like going backwards through the operation there. All right, so I want to talk about a little bit shifting the discussion to why we care about logs. There's so many reasons I can't give it all in one lesson, but I'm going to give you a couple of really big ones right now. So far, we've been doing a lot of base 2 logarithms. The reason we're doing base 2 logarithms is because it's easy to calculate. But really, one of the most common logs that you're going to run into is base 10 logarithm. In fact, when you say the word logarithm, if you don't specify a base at all, most people are going to assume that you probably mean a base 10 logarithm. And later on in the class, we're going to talk about base E logarithms, the special number E. We'll talk about that later. We're not going to get into that now. That thing is called the natural logarithm. We'll talk about that much later. For now, let's focus on the other special logarithm, which is the base 10 logarithm. All right, so base 10 logarithms are really important. So let's talk about that. Base 10 logs. All right, so what I mean when I say base 10 logarithm is if you have a function, f of x, equals 10 to the power of x, the base is 10, then its inverse is going to be a logarithm, but the logarithm has to be a base 10 as well. Logarithm base 10 of some variable x, okay? So you see, in order for these to be inverses, the bases have to be the same across the exponential and across the logarithm, otherwise they're not inverses of each other. So let's talk a little bit about some base 10 logs. Let's say I have log of the number 1. Notice I didn't write the base 10. If you see a log without any base written at all, you just pretty much assume it's a base 10 log. That's how common it is. If you see a base there, you have to use the base, but if you don't use a base at all, if you don't see a base at all, it's a base 10 log. What is the log base 10 of the number 1? Well, what we know is that that means that's exactly the same thing as this, base 10 logarithm of 1. And what this means is we take the base of 10, raise it to some unknown power we're trying to calculate because the log gives you the power back, equals 1. So my question to you is, what value of x works? And that means x has to be 0. Why? Because 10 to the 0 is 1, right? So what we've learned here is that log of the number 1, base 10 log of the number 1 is 0, okay? What I'm going to do is calculate a few of these things going down the page, and I'm going to draw some really important observations as we go down here. So that was the log of the number 1. Let's take a look at log of the number 10. Again, it's a base 10 log because there's nothing written there, but you can kind of assume that it is. This is the exact same thing as writing base 10 logarithm of the number 10. So what does this mean? It means the base to the power of something has to equal this number. Now what does this exponent have to be equal to? It has to be equal to 1. The only exponent that works is 1. So that means that the log of the number 10 is equal to 1. So we figured out the log of 1 is 0, base 10, and the log of 10 is 1, again, base 10. So let's do a couple more examples down the page here. Let's go and do the log of 100. Okay, how do you figure this out? Well, you know it's a base 10 by now. So 10 to the power of something is 100. What does this exponent have to be? The only way this works is if x is 2, because 10 squared is 100. So we've learned that log of 100 is equal to 2. So I'm generating a pattern here, and now that we understand what we're doing, we're going to go down the page a little bit faster. If the log of 1 is 0, and the log of 10 is 1, and the log of 100 is 2, what do you think that the log of 1,000 will equal to? Well, it's going to be 10 to the power of something is 1,000, so it has to equal 3, right? What do you think the log of 10,000 is going to be equal to? Well, 10 to the power of something is 10,000, has to be equal to 4. You see what's happening? You started out at 0, and then it goes 1, then it goes 2, then it goes 3, then it goes 4. So as I take the logarithm, I've multiplied by 10. I'm taking the logarithm of something 10 times bigger. And then here I'm taking the logarithm of 10 times bigger still. And here I'm taking the logarithm of 10 times bigger still, 10 times bigger still. Every time I go up times 10, the logarithm just goes up by 1. You see, I'm taking the logarithm of something 10 times bigger every time, but the logarithm only goes up from 0 to 1, to 2, to 3, to 4. And you can generalize that. What if you do something that's not a perfect little times 10 thing. Let's take the logarithm of 20,000. That is not 10 times bigger. It's not 10 times bigger. That's only 2 times bigger. What do you think you would get? Well, what you're going to have is you're going to have 10 to the power of something is 20,000. When you run that in a calculator and figure out what this exponent is, you're going to get 4.3. Now, I've rounded it to 2 decimal places. But you see, it's just a little bit bigger than this one. See, the logarithm of 10,000 was 4. The logarithm of 20,000 was just a little bit bigger than 4. Okay, what do you think the logarithm of 150 would be? Just to pick a totally different number. Well, what you would say is 10, the base 10, to the power of something is 150. When you run that through the calculator, you're going to get 2.18. And I'm getting to a point here, I promise. I have one more to put on here. What about the logarithm of 1,700? When you run that through a calculator, you're going to get 3.23. Okay? What I'm trying to get you to say is something that I honestly didn't really realize about logarithms until well beyond I had learned them. It's something way in the future. I finally understood what logarithms really are. I don't want to say their only use, but one of their main uses. Okay, when you run a number through a logarithm, what the logarithm really is doing is it's giving you the exponent back. That's what I've been telling you over and over again. But notice that for 1,000, what's happening is the number you're getting back is the number of decimal places past the first position. When you take the log base 10 of 1,000, you're getting the 3, it's telling you, hey, there's 3 digits past the number 1. When you take the log of 10,000 and get a 4 back, it's telling you, hey, there's 4 digits past the 1. When you take a log of 100, it's telling you, hey, there's 2 digits past the 1. Hey, there's only 1 digit past the 1. Hey, there's no digits past the 1. So the logarithm base 10 is really telling you how big the number is, how many digits it is. It's ignoring all the details. Notice that the log of 20,000 is telling you, hey, there's 4.3 digits. That's kind of a little weird because there's 4 digits after here, but it's basically telling you how close you're going to be, because when it gets to 5, that would be 5 digits past. Right? It's at 20,000, you have to go 20 and 40 and 60 and 80, then you would get to 100,000, that would be 5 digits past. So this is telling you you're getting fractionally a little bit closer to that next decimal place, that next 0 in the number. It's telling you how much closer you are to that, but it's basically reporting back how many zeros or how many digits you have in the number past the first position. Here you had none past the first position. Here you had 1 past the first position, 2 past the first position, 3 past the first position, 4 past. This is just a little bit more past 4. This is a little bit more past 2, so it's 2.18. This is a little bit more past 3, getting close to, you have to get up to, 10,000 to get to the next one, and you're getting a little bit closer, and the decimal part of it is telling you that. So it tells you the number of digits. So if you have numbers where you don't care about the exact value of the number, you just kind of want to know roughly how big things are, then a logarithm is a perfect thing because it's going to throw away all of the, I don't want to say throw it away, but it's going to tell you basically how big the number is, how many digits the number has, without all the details of the actual number there. You might say, why do we care about that? Why don't we just give you the number? Well, a great example is the Richter scale of earthquakes. You always hear in the news 6.2 on the Richter scale, 5.3 on the Richter scale. And it also doesn't really become very clear what those numbers really mean. But you have to remember that every time we multiplied by 10 of the number, the logarithm of it just went up by 1. So what we've learned here is since the Richter scale is logarithmic, if you see a 4.0 on the Richter scale and a 5.0 on the Richter scale, it doesn't seem like very much. But really that means it's 10 times bigger. A 4 on a Richter scale and a 5 on a Richter scale is not a little bit different. It's 10 times bigger. How do I know? Because the difference between 3 and 4, or let's go back to 3 and 4 versus 4 and 5, the difference between 3 and 4 on the Richter scale is actually 10 times bigger in energy. Earthquake is measured in energy, right? So if you had a situation in an earthquake, right? I'm not an earthquake scientist, okay? But here you're basically measuring energy. Energy of the earth coming out in terms of, this guy here. Let's talk about versus time. So energy versus time. An earthquake probably starts, small, and it gets really powerful, and it gets really small again, right? So what you have with earthquakes is there is a huge amount of difference in energy released, right? So what might happen is you might start out really, really, really low on this energy scale. It might be really, you can't even read it on this graph. And you have a little spike here, a little bit bigger spike. And then the main part of the earthquake comes, it goes really, really big, really, really big. And it has junk down here you can't even read. And then it's really, really big again, really, really big again. And then it gets off the chart and it comes back down like this. You see, a graph like this isn't that useful to us. I mean, it is useful. It does tell you how big everything is, but the problem is I can kind of read these, but I can't read any of this stuff down here because at this scale, the tiny little wiggles at the bottom are impossible to read because they're just so small compared to everything else. And the reason they're so small is because there's a huge difference in energy released in the beginning of the quake to the middle of the quake, right? So what you need is a way to tell me how big these different parts of the earthquake are, or how big different earthquakes are, without using the actual numbers, the actual energy numbers, because the energy numbers are going to be huge, 100 million trillion, and then another earthquake might be 100,000 or 5,000. And that number is just so different that you can't graph it like that. So what we do is instead of reporting the energy numbers of the earthquake, we take the logarithm. Right? Now, the actual Richter scale is a little more complicated than this, but basically you're taking the logarithm. So notice that when we multiplied, like the difference here in energy here to the energy here might be a difference of 100 or a difference of 1,000. It's hard to graph that, but the difference between 100 and 10,000 is just a difference of 2 points on a logarithm scale. So actually we graph these earthquakes on what we call logarithm scales. We take the logarithm of all the data, and that basically gets rid of all the details, and it just tells me how many digits, because the numbers are so huge. I only care about how many digits are in there when it's little versus when it's big. So the actual Richter scale looks something like this. So it's called Richter scale. And again, I'm not an earthquake scientist. I grabbed these right off Wikipedia, right? So a 1 on the Richter scale is called a micro. You basically can't even feel that. A 2 on the Richter scale is called a minor earthquake. 3 is also characterized as minor. You probably feel that, but you're not going to be that scared by it. A 4 is going to be called a light. Light, you're going to have some damage, but probably not very much. A 5 is going to be moderate. A 5 is when you're going to start reporting these things on the news. A 6 on the Richter scale is a strong. A 7 on the Richter scale is a major. Right? An 8 on the Richter scale is great. A 9 on the Richter scale is total devastation. Right? A 9 point anything. Now there's no 10 because it only goes to 9.99 or whatever. Okay, but basically anything above a 9, your city is flattened. Major, major damage. I mean, way more major than a typical earthquake. I mean, the reason that these numbers don't often convey the strength here is that because the number 2 and the number 4, they don't seem so far apart. However, between the number 1 and 2, this is times 10 bigger. Between 2 and 3, this is times bigger than that again. So that means between 1 and 3 is actually 100 times bigger because 10 times 10, right? This is times 10. This is times 10. And then from here to here is times 10, and then you have times 10. You get the whole idea. Times 10, times 10. So if you're looking at the difference between 1 and 2, that's 100 times bigger. Between 1 and 3, I'm sorry, 1 and this one right here, this is 100. This would be 1,000 times bigger. This would be 10,000 times bigger. Right? And you could go down the calculation and figure out how much bigger a 9 would be than a 1. But that's why when you see on the news, you might see a 5.3 on the Richter scale, and that's bad. But a 6.3 is way, way worse because it's 10 times bigger, okay? And that is one of the biggest uses of the logarithm is in practical use that you would see in everyday life. But there's many other examples. I can give you from chemistry, I can give you from physics or whatever, but this is the one that you'll actually probably see on TV. And it all goes back to the fact that when you start taking logarithms of numbers, if you on a base 10, then you start multiplying by 10, then the actual logarithms are just giving you the number of digits back. So they're only going up by 1 each time, every time you multiply by 10. So that is the concept of what is a logarithm. I hope that you can understand what a logarithm is. It's basically the opposite, also what we call the inverse of an exponential function. Logarithms are not going away. Some students don't like them, but you're just going to have to get used to them. My best advice is just to, when you start to see a logarithm written down anywhere, just immediately convert it to exponential form, because most people are more familiar and comfortable with an exponential function. Logarithms get crazy, and people get crazy, they don't understand how to deal with it. But we have to learn it because later on we have laws of logarithms, how to add logarithms, how to multiply logarithms. They're not going away. So make sure you understand this, solve these problems, draw these graphs. Follow me on to the next lesson. We're going to start simplifying expressions that have logarithms, and we'll be using this definition, this exponent inverse definition along the way. So follow me on there. We'll continue learning about logarithms in math.